Honored to have the chance to address on this special occasion. The topic of my paper is EmbRace, accelerating sparse communication for distributed training of deep neural networks. The outline of my talk is as follows. First, I will introduce the background and the motivation. A deep neural network, or DNN model, is usually constructed by a sequence of layers and trained by repeating iterations. Data parallelism on distributed GPUs is the most widely used parallel strategy to reduce the overall training time. In data parallelism, gradients are communicated from all workers to keep models synchronized. Unfortunately, with the fast increasing size of models and the number of workers, communication overhead becomes the main performance bottleneck of distributed training. Communication acceleration has been extensively studied in the literature. However, this approach mainly focuses on dense models. In natural language processing, or NLP models, embedding metrics are generally adopted for feature learning, where each row maps a word to a vector like fingers on the left. When training embeddings with patches, a small subset of vocabulary is used, and only the related rows would be updated. Therefore, the gradient of the embedding matrix could be sparse. The table on the right shows some popular NLP models with their model size, embedding table size, and the ratio of embedding tables. The massive parameters of embedding and its large proportion introduce large communication overhead and seriously restrict the training scalability. Therefore, communication embedding in NLP model with both high efficiency and good scalability become one challenge for us. Overlapping communication with computation could reduce the communication overhead and accelerate the distributed training. Recent researchers use communication scheduling to achieve this. The key idea is to adjust the communication order of DNA layers to hide more gradient communication by computation. However, existing scheduling approaches are only designed for dense models, treating embedding table as an entire scheduling unit. As shown in the upper figure, the communication of zero element in the embedding would involve unnecessary communication and slow the execution of forward paths. Moreover, parameter updates of embedding table are element-wise, relating to the token which are appeared in this training iteration. Based on this, as shown in the layer figure, developing an exhaustive scheduling method for NLP tasks to overlap more communication with computation become another challenge for us. Next, we introduce our approach. EmbRace is a distributed communication framework for sparse model at top PyTorch and Harvard. To achieve efficient communication in NLP models, we design a sparsity-aware hybrid communication, applying hybrid communication strategies. For sparse tensors, we apply model parallel and all-to-all to specifically speed up their communications. To efficiently schedule the communication of sparse NLP models, we introduce 2D communication scheduling. With the dependency graph, we could assign priorities to all dense gradients and each row of sparse gradients in the model, and hold a priority queue to perform all communication operations. Let's explain how sparsity-aware hybrid communication works first. Collective operation to all is useful in recommender system training. We bring it with model parallelism to data parallel NLP training for pursuing the efficiency of sparse communication. Compared to the row-wise partitioning, the column-wise partitioning method will scatter the embedding vectors, keep a whole corpus of vocabulary in each part. These uniform partitions will get the same amount of requests and own balance loads naturally. The data flow of embedding communication is on the right finger. All-to-all communication is called twice. One is after forward path of embedding for redistributing embedding lookup result, and another is after backward path for exchanging embedding sparse gradient. Apart from sparse data, we employ all reduce to communicate dense models. These dense parts are treated as an individual dense model so that we could utilize the popular distributed framework Harvard. Firstly, we show the efficiency of our implement theoretically. Fingers shows the example of communicating sparse data with different primitives. The upper table lists use the symbol, and the lower table shows the theoretical result. From the result, all-to-all and all-reduce maintains good scalability, while communication will not be strongly impacted by the GPU number, while altogether is approximately linear to the GPU numbers. Hence, in the distributed training environment and for sparse tensor, the all-to-all method will be the best in theoretical. In practice, different communication algorithms, network topologies, and message size will influence the performance greatly. We conduct communication efficiency tests on gradients with different sparsity. On two nodes with 4 RTX 3090 GPU each, all-to-all outperform other methods when the sparsity is greater than 40%, while the sparsity of NLP models could exceed 60% easily. On four nodes with 1 RTX 3090 GPU each, all-to-all is the best method on all sparsity. Reason work only reduce implement a sparsity-aware or reduce algorithm, but only supports each node use one GPU. Therefore, after considering both theoretical and practical results, all-to-all with model parallelism become our sparse community solutions. The following is the 2D communication scheduling. In order to scheduling NLP model properly, we explore the modular dependency at first. Taking translation models as examples, they can break down into four major modules: encoder embedding, encoder blocks, decoder embedding, and decoder blocks. With our sparsity-aware hybrid communication, the dependency between modules starting from the backward path are shown in the right figure. By default, the order of forward path and backward path are inverse, and the communication will follow a first-in, first-out queue. The execution timeline of default scheduling are shown in the lower figure. The gradient communication will prevent starting of the forward path of next iteration, and the embedding lookup result communication knows the forward path of encoder and decoder blocks. To deeply overlapping, we firstly schedule the communication in horizontal. The communication of dense block is scheduling with a priority queue, so that forward paths could start earlier and could overlap communication operations. We observe that the computation load are more even on NLP models, so according to the forward order, we could assign priority in block level. Figure shows an example execution timeline of black level horizontal scheduling compared to the default timeline. The communication quantity is the same, but dense communication are split to parts and some parts are overlapped with forward paths. However, limited by the bandwidth and the module dependency, there is some styling at backward and some hunts between forward. There are potential reductions in embedding sparse gradient size. First is the duplicate values in sparse gradients, which comes from the padding and duplicate words. These multi-value elements could be collapsed into a single value, and hence reduce the gradient size. The other is we observe that, with the data changing among training steps, different corresponding embedding rows would be updated. This shifting promotes as the minimum dependency of the next forward path is the embedding rows of the next data rather than the whole embedding. Hence, when we consider communicating sparse gradient in this iteration, we divided the gradients into two parts, a prior part and a delayed part. The prior part contains the gradients related to the intersection of the data between the current and the next iteration, and we assign it with the highest communication priority. In contrast, remaining gradients compose the delayed part. The table shows the average sparse embedding gradient size in vertical sparse scheduling. Compared to the original gradient size, the prior part is much smaller. Here is an example of vertical sparse scheduling. The duplicated words are collapsed, and the prior data are picked out, such as the word robot, which is required by the next training iteration. Vertical sparse scheduling calculation require a considerable computing resource. The GPU idle time after backward pass is a good occasion. The timeline after 2D communication scheduling is shown in the lower figure. The embedding gradients are reduced, and the sparse communication is done in two parts. The first is the prior part. The forward pass starts immediately after communicating the slight prior gradients, resulting in better overlapped and efficient data parallel training. Next, come to the evaluation baseline are involved in our experiments. Bad PS, Harvard all reduce, Harvard all gather, and parallax. Figure shows the overall training throughput for LM, GMT8, transformer, and bird base on 4, 8, and 16 GPUs. The numbers are speed up of EmbRace over the base baseline, with the contribution of the sparsity-aware hybrid communication and 2D communication scheduling. EmbRace achieves a 1.02 times to 1.77 times speed up on RTX 3090 nodes and 1.09 times to 2.41 times on RTX 2080 nodes. Computation store is defined as the computation store time caused by communication during the training procedure. For EmbRace, the computation store consists of the vertical sparse scheduling computation and the communication that are not overlapped by the computation. While for other approaches, computation store is only the non-overlapping computation overhead. As shown in the figure, EmbRace reduces at least 49% computation store in LM and BERT-based model, and reduces at least 26% computation store in GMT and transformer. To analyze the effectiveness of our optimizations, we carry out the ablation study with all 4 benchmark models on RTX 3090 nodes. When compared to the Harvard all gather and Harvard all reduce, results of EmbRace without scheduling could show the performance gains of sparsity-aware hybrid communication. To demonstrate the effect of 2D communication scheduling, we could compare the training speed of EmbRace with and without scheduling. Figure shows the experimental results. Both techniques of EmbRace could bring remarkable improvement. To demonstrate the scalability of EmbRace, we compare it with the baseline, which has the best scalability. We also use the throughput on 4 RTX GPUs as the benchmark, then calculate the ideal linear result. As the figure shows, EmbRace get better scalability. Due to the limitation of the cluster size, we did not test on more server nodes. We expect that EmbRace will have more significant advantages on more GPUs because of the better scalability. In conclusion, first, we present EmbRace, an efficient distributed sparse communication framework for NLP model training. EmbRace introduced sparsity-aware hybrid communication that use all-to-all with model parallelism to raise the sparse communications. And we designed 2D communication scheduling to achieve a zero overlapped communication schedule. EmbRace achieves up to 66% communication store reduction, up to 2.4 times training speed ups, and better scalability. That's all for me. Thank you for listening.